Hello and welcome. We are learning laws of motion, and in this video we are going to learn about the drag force. So what is a drag force? We know that a fluid is anything that can flow. It can be a gas or it can be a liquid. So when an object moves through a fluid or there is a relative motion between the fluid and object, the object experiences a force which opposes their relative motion. So if we have an object moving in a fluid in this direction, this object experiences a force which is called the drag force. This force is given by D equal to half CD rho F A B square. The CD is the drag coefficient, rho F is the density of the fluid, A is the effective cross-sectional area of the object. In other words, it is the area of the projection of the object in the direction of the flow. And in this case, it is simply a circle. It is the area of a circle whose radius is equal to the radius of the object. This velocity v is the relative velocity between the fluid and the object. The drag force always points in the direction in which the fluid flows relative to the body. So in this example, this is the direction of the motion of the object. Therefore, the fluid direction relative to the object is in this direction, and this is the direction of the drag force. The drag coefficient is always less than 1. Suppose that an object falls through rest through air at any instant. Let the acceleration of the object be a. At that instant, the forces that are acting on this object are the gravitational force and the drag force. The net force on the object being d minus mg. So at that instant, when the object is falling from rest through air, the net force is d minus mg, and this is equals to mass of the object times the acceleration of the object. Now we already know that the drag force is proportional to the square of the velocity, square of the relative velocity between the object and the fluid. So as the velocity of the object increases, the drag force increases, and it so becomes that the drag force may become equal to the gravitational force. So when the drag force becomes equal to the gravitational force, at that moment the acceleration of the object is zero. At this moment, acceleration of the object is zero, and then the velocity of this object becomes constant. This constant speed or velocity of the object is called the terminal speed. This constant velocity of the object falling through air is called the terminal speed. To obtain the value of the terminal speed, we put the value of d in this equation. We put the value of d in this equation. So d is equal to half cd rho f a vt square, where vt is the terminal speed and this is equal to mass times v for acceleration. From this we can calculate the terminal velocity as square root of 2 mg divided by cd rho f a. This is the terminal speed of an object which falls from rest through air.
Now we'll take an example. In this example, a spherical raindrop of radius r equal to 1.2 mm falls from a cloud. The height of the cloud is 1000 meters above the ground. We are required to find the terminal speed of the raindrop. We can take drag coefficient as 0.5, water density as 1000 kg per meter cube, and density of air as 1.2 kg per meter cube. So first we will find the mass of the raindrop, which is equal to volume times density. The volume of raindrop is the volume of a sphere, which is equal to 4 by 3 pi r cube. Therefore mass of raindrop is 4 by 3 pi r cube times density of water, that is rho w. The gravitational force acting on the raindrop will then be equal to mass times free fall acceleration, and then the terminal velocity will be equal to v equal to square root of 2fg divided by cd rho a, which is the density of the air, times the cross sectional area of the raindrop, which is equal to pi r square. We can put fg from here to obtain vt equals to square root of 8 pi r cube rho w g divided by 3 cd rho a times pi r square. This pi we can cancel, this r square also gets cancelled, and there only remains r in the numerator. Therefore, Vt becomes square root of r rho wg divided by 3 cd rho a. Now we can put all the variables and we obtain Vt as square root of 8 times 1.2 10 to the power minus 3, which is the radius of the raindrop, 1000 is the density of water, 9.8 is the free fall acceleration g, zero point 0.5 is the drag coefficient, and 1.2 is the density of air. From this we obtain Vt as 7.2 meter per second. Therefore, the terminal velocity of the raindrop falling through air is 7.2 meters per second. Suppose that there is no air drag, then the velocity of the raindrop will continue to increase until it reaches a maximum value just before hitting the ground. For comparison, we wish to calculate the maximum velocity of the raindrop before hitting the ground. We will use this equation of motion, v square minus u square is equal to 2gh. U is the initial velocity, which is equal to 0, h is the height of the cloud, and v is the final velocity of the raindrop before hitting the ground. From this we obtain v square as 2 into 9.8 times 1000, which is the height of the cloud. From this we obtain v square as 19,600, and from this we obtain v as 140 meter per second. Therefore, in the absence of any air drag, the raindrop speed reaches to about 140 meter per second before hitting the ground, and when there is air drag, the maximum velocity that the raindrop reaches is 7.2 meters per second, and this is the terminal velocity of the raindrop.
That's all for today. In the next video, we will learn about the force acting on an object when it is in a circular motion.